Here are some quick notes on the planetary mass-radius relation to accompany Chapter 6 of To Build a Star. What I want to do here is just expand a little bit on something that was briefly alluded to in the book in problem 6.8. So in Chapter 6 of To Build a Star in problem 8, what we do is we calculate a mass-radius relation, and we find for a certain set of conditions that the radius goes as the square root of the mass. And we're asked or encouraged to compare that to the mass and radius of different solar system objects. And so we'll see that what we're doing is actually coming up with a pretty good approximation for the mass-radius relationship for low-mass planets. So what we did in this problem is we assume that the Coulomb repulsion basically dominates. So it's a very dense environment and rather cold, and so the Coulomb force is basically what matters the most. And so your density is set by the atomic spacing. So atoms are packed roughly an atomic distance apart, and we approximate the size of an atom with the Bohr radius. Then what we do is we set the electron degeneracy pressure equal to the central pressure we calculated from the virial theorem, just way back in Chapter 2. So this is essentially To Build a Star problem 6.6. And what we do is we plug in this density to our degeneracy pressure formula, and then we find a parabolic relation between the mass and the radius. We find the radius goes as the square root of the mass. So what I want to do here is do a more detailed comparison than is alluded to in the book, where we can see that it does amazingly well. So this is the planetary radius and Earth radii versus the mass and Earth masses. And if you tilt your head, you see this parabolic relationship as predicted. There's some more curves from more sophisticated models here. And the data, though, for these planets fall on this line. So you see some solar system objects here and then exoplanets as well. So for these mostly solid low-mass planets, this relationship does quite a good job. Now what you can also see from this plot is that if you do a more sophisticated job of what kind of matter do we have, what would its atomic spacing be, then you get different curves. And so for instance, if you just had pure core, no liquid-like material at all, then you have this more compact mass-radius relation. And if instead you introduce more liquid layers like a mantle, you get a less compact object. And then if the thing's pure water, it's a quite large radius for a given mass. And what that means is by getting a mass radius measurement for a planet, you can actually say something about the composition of that planet, which is kind of amazing. That would then complement any information you may get from spectroscopy of the atmosphere during a transit event, for instance. Now, for low mass planets, that's perfectly fine. Once your mass increases to a certain point, then the Coulomb repulsion now is getting pretty stiff competition from electron degeneracy pressure. This pressure begins to take over as the dominant factor of the mass-radius relation. If you have a large amount of mass, like a star's worth, a sun's worth, then you're dealing with a white dwarf. And we showed in To Build a Star exercise 6.6, or you'll find this soon, that then the radius goes as something like 1 over the cube root of the mass. However, somewhere in between this point, so in between the previous slide where you have the square root of the mass, where it's all Coulomb, and in between that and the region where it's all electron degeneracy pressure in your white dwarf, these two things are competing. And what happens is you go from having this parabolic relationship that we talked about, and somewhere around 100 Jupiter masses or so is where there's stiff competition, and now your radius is roughly independent of your mass. And these data here, these are data from exoplanets for the most part that are mixed in here. And again, in units of Earth radii and in Earth masses. So you see this turnover. Exactly where this turnover would be and exactly why it would be there is a matter of current research, and that's one thing exoplanet data is used for. So why would we care about that? It's because this mass-radius relationship basically tells you about the equation of state of matter at extremely high densities, but much lower temperatures than stars. And additional exoplanet data is coming in all the time. Exoplanets, I would say, are a current hot topic in the field, and probably will be for some time to come, just based on the advances in telescopes. As far as I can tell, exoplanets.org is updated extremely frequently by experts in the field. And for instance, we can look at the world data of radii versus mass. In this case, we're looking in units of Jupiter radii and Jupiter mass. And still, you see for all the data, there's some big error bars on some of these, but for the most part, you have this parabolic relationship until you get up to something like the size of Jupiter, and then your radius is sort of flat with your mass, or maybe even decreasing a little bit. And again, this is something that's often done is for these individual exoplanets, as we can compare them to theoretical predictions where you assume different compositions. And for instance, you can infer that certain exoplanets are gas giants. Due to observational biases, a lot of the exoplanets that are known right now, and pretty much all the early ones, were the very large planets, gas giant type planets, just because the small ones are difficult to find. And now we're starting to discover more, I'd say Earth-like rocky planets, so things that are closer to down here. So this just has the solar system and exoplanets. So with that is it for these quick notes on the planetary mass-radius relation, and that is it for now.